This is an exercise on induction motors. This is an induction motor with the following ratings. It is rated for 480 volts line to line, 250 horsepower, rated output mechanical power 60 Hz, 4 poles. It is connected in a Y, and the parameters per phase and referred to the stator side are given in this table: R1 X1, R2 prime, X2 prime, and Xm. We know that the motor is taking from the source 111.1 amps and a power of 70.1 kilowatts. Determine what is the speed of the motor N in RPM. The first thing I do in an exercise like this one is to draw an equivalent circuit of the one phase I will be working with. This circuit. I have copied the values of R1 X1, X2 prime, Xm, and R2 prime to the circuit. The applied voltage is, of course, one of the phases of a Y connection is the line-to-line voltage 480 divided by root 3. I will use this voltage as my phase reference, 0 degrees. The input current is given as 111.1 amps, but the question is, what phase? To find the question of what phase, we are given the datum that the motor is taking 70.1 kilowatts. That is a three-phase power of 70.1 kilowatts. From there, we can compute what is the phase difference of the current and the voltage. Like this, the input power is 3 times that applied voltage times the RMS value of the current times the power factor. But the input power is 17.1 kilowatts. From there, we find that the current is lagging behind the voltage by 40.63 degrees. How do I know that this phase is lagging? Because this is an inductive circuit, of course. So the input current is 111.1 with a phase of negative 40.63 degrees. Those are amps. But now that I have that current, I can compute this voltage Vm with respect to this reference. The input minus this drop. The input voltage minus this impedance multiplied by the current, phase and all. That voltage is 151 with a phase of negative 18 degrees. That is the voltage across that. With that voltage and this impedance, we can determine the magnetization current. Let's move down a little bit like so. That current is this voltage Vm divided by the impedance J, 25.7, is 5.9 amps with some phase. This is this current. With those two currents, I can compute the current of the rotor referred to the stator I2 prime, like so. Current of the stator minus magnetization is 109 amps and some phase. That is that current. Now, the actual voltage in here, Vx, is Vm minus this drop in this reactor. Vm minus that current that we just computed times the reactor J, 0.463, that is 142.5 volts, right here Vx. But if we know that voltage Vx and this current I2 prime, I divide them and can compute this resistance. And from there, we can solve for S. And that is exactly what I'm doing here. That resistance is Vx divided by I2 prime, 1.3 ohms. And from there, we determine that the slip has to be 0.25 per unit, which is a lot, 25% away from the synchronous speed. The velocity of the motor is 1 minus s times the synchronous velocity in RPM, which is 3600 divided by the number of parallel poles, 2, that is 1800 times that, 1350 RPM. That takes care part A. Now, what is the torque of the load? Because we are told that the machine has negligible rotational core losses, T load is the induced torque, and the induced torque is given by that famous formula we saw in class, P gap divided by the synchronous velocity in radians per second. P gap is just 3 times Vxi2 prime, that is 3 times the power in this one resistor, and the synchronous velocity is 2 pi 60 divided by the number of parallel poles, 188.5 radians per sec. Here is the P gap for comparison with your results, and the torque of the load is 247 Newton meters. Now the question is the motor operating in its stable or unstable region? That is, to the left or to the right of Tmax? To answer that question, because we know that S currently is 0.25, we need to compute S max. And to do that, we need the Thevenin equivalent of our circuit, the Thevenin equivalent seen by this resistor, the Thevenin equivalent of all that is enclosed by that red cloud. That is a simple matter of computing V Thevenin and Z Thevenin for that circuit seen from the point of view of the resistor, and they turn out to be 266 volts and some impedance that is written down here. And then we know that we have maximum torque at a slip that is given by R2 prime divided by the absolute value of that Thevenin impedance as we saw in class, that is max. The slip for maximum torque is 0.2, 0.2 down here. But the actual S, the actual slip is 0.25, so that means that we are over here on the unstable zone. Well, remember that this part of our diagram, all the way up to the S max, is unstable, and the part on the right hand side, this is the stable zone. So we are operating in unstable mode. The last question is how much external additional rotor resistance we need to add through the slip rings and brushes to bring the maximum torque to standstill conditions, that is, to the point where the machine is not moving anymore. If the machine is not moving anymore, the slip is 100%, 1 per unit. So for Tmax at this value, the total resistance of the rotor, R2 prime plus the additional resistance, has to be equal to the magnitude of the Thevenin impedance that we computed before. Solving for the additional resistance, that gives us 1.3 ohms. And that is the solution to this question. Thank you very much.